Okay.
Hello, we are doing the group activity number 2. I am the chairperson for this video. So for our group, we went over the filtration quiz and video on our own, and we're just going to go through the questions. So question number 1, let me pull it up here. What is the primary purpose of diagnostic filtration in radiography? Does anyone want to volunteer to answer?
That's to decrease patient dose.
That's also what I got. I just put 2 lower energy photons could damage the cells and then could go on to cause cancer or harmful effects.
Did you want to share your
Anyone add anything?
did you want to share your screen so we can kind of look at the question at the same time and then we can kind of look at the answers?
Yeah, we can do that. How do you?
I think you have it blocked, Felipe. I
I,
tried to do it earlier.
I looked it right now. It should be open.
Okay.
Yeah. Can everyone see that?
Love it.
Oh yeah. Oh no, you can see which ones I got wrong. Ignore those. So yeah, that's number 1. Okay, number 2. Anyone?
For number 2, what type of X-ray photons are virtually removed by filtration? Is the low energy photons. So kind of like what we learned in the past when if there's a like filtration just removes like the low energy photons so that they could get a higher, the most strong, I guess, like photons to the patient.
Yeah. I like that the video also related it to kind of like a water filter. It gets rid of the smaller, like the part that we don't need, and then keeps the bigger, larger photons.
Yeah, like gets rid of like all the unnecessary
Yeah.
radiation.
Anyone else want to add anything, or is that kind of we all agree?
Yeah, I honestly hesitated about this one, even though the video did not mention it. I was this close to clicking characteristic photons just because of like how we talked about it in class, how it has a low energy in general. And I was like, filtration, that'll take away characteristic as well. But then I was like, oh wait, never mind. They didn't talk about it in this video, so low energy photons.
Wait, but is characteristic the strong one or the I thought it was Bremsstrahlung was the lower energy.
Yeah, Brem is the lower energy. I think characteristic is the stronger energy.
Really?
So
I think it was the reverse.
yeah, if it was that, it would be Bremsstrahlung, and then maybe it would like be right in this question.
Okay. Okay.
I'm just guessing. I don't know.
You got it right, so
Okay. Well, I mean, okay, here we are. Number 3, I got wrong. Primary patient dose measurement is influenced by filtration. So I think this one was like tricking me up because I was thinking patient dose with like effective dose with the tissue, how we learned in physics, but it's more of the skin dose. Does anyone know why it's specifically the skin dose or?
I would think the entrance skin does because of the filtration. It kind of blocks out, like earlier you said, the water filter. It's like taking out the bad, leaving the good. So it's like the bad that goes from the skin dose, basically, kind of like the scatter.
And then I guess that filtration might remove some of the low energy, but it won't remove all of them. And so not all of the um, X-ray beams that are getting to the patient are going to be, like for example, like 100 kV. Some of them might still be like in the high 80s, and they might not have enough energy to penetrate, and so they're mostly going to get absorbed by the patient's skin rather than making it to the plate. That
I
one
was
is
thinking, yeah, I could remember this one too, like the skin, it's like the first thing that hits the patient for the patient dose. I don't know if that might trick me up for later, but what does it say? Smaller effect on teeth. No, it doesn't really say why it's not effective dose. Does anyone else want to add anything to this one?
Mhm.
No? Increasing the thickness of filtration has what effect on the patient's entrance skin dose? Assume no other technical factors are changed.
It's just kind of like going off of that, the whole round robin thing he wants us to do. Like,
Mhm.
um, I think this one is similar to that other question, like, well, actually, the past two questions, what does the filtration do? It reduces the low energy photons. Usually one of those filtrates is like aluminum. And then here it's asking us, the thicker the filtration, what affects that. So of course, if you have like a thicker filtration, so like a thicker aluminum um, filter, then it's going to have those low energy photons are going to have a harder time to penetrate, and so thereby decreasing the entrance skin dose to the patient and maintaining those higher energy photons that are going to get all the way through the patient and onto the plate. That's what I'm thinking, though. But
So would the filtration and the entrance skin dose be inversely proportional?
correct. Yeah, the thicker the filtrate, the lower the patient dose.
Mhm.
That's a catch, actually. I like that. I like that we said that.
Yeah.
Um, yeah, so the thicker the filtration, the less will get through, therefore decreased entrance skin dose.
We have 10 minutes.
And then Felipe, you already said the answer to this one actually, just barely, that it's aluminum
Mhm.
Oh,
the most commonly used.
Jumped ahead, but we still got it.
sorry.
Yeah.
Me and the big mouth. Sorry.
Yeah, I talked about this in class too. I learned in this one though that it was because of the low atomic number.
Mhm.
I was
Mhm.
thinking because it was a high atomic number. I never really looked back at the periodic table for this. So because we want the low ones, the low photons absorbed by the aluminum can only absorb the low ones with that atomic number. I don't know if that makes sense what I just said, but
Yeah.
if we had a higher atomic number, it would take too many of the high photons. So we want only the low ones.
I know. Would any photons go through if it was higher than,
Yeah.
yeah, than aluminum? Yeah.
So like lead would totally block it. I don't know what the
Nothing would get through tungsten.
Mhm.
I've never heard of bismuth.
Tungsten?
Bismuth.
I
Oh,
don't know what that is is that the one that's 83 though that we were just talking about earlier before we started the video?
I think so.
believe so, yeah.
Um and then tungsten, I'm curious what that would do.
Well, I think it would literally just absorb the majority of like the photons from the beam, just because it's the atomic number is so high.
Mm-hmm.
From what I remember seeing it in the book, like Hugh talked about it, he was like memorized tungsten. So I was like looking at it, and the atomic number is super high.
He was kind of throwing me off with a tungsten target. I was like, will it
Yeah.
make more? But okay, so those all would absorb too much.
Mhm.
How does increasing filtration thickness affect the quality of the X-ray beam? So this is another relationship. Does
Mm-hmm.
anyone want to comment on this one?
I think it's the one that Kimberly was talking about.
Mhm.
Yeah, I think just because it absorbs the low energy photons, it means the beam that's remaining is of a higher quality.
Mhm. All right. I think the next one's kind of similar too. So if we decrease filtration thickness, what will it do to the quality? Decrease quality.
Mm-hmm.
And then this one is similar, but it's asking now the quantity. So if you increase the thickness of the filtration, how much of the photons will get through?
Yeah, so this time it's an inverse relationship.
Mm-hmm.
Mm-hmm. We
Yes,
increase the thickness, decrease the quantity.
Yeah, because it's absorbing more low energy photons.
Mm-hmm.
Okay. And then this one tricked me up. So the following illustration represents the energy spectrum of an unfiltered X-ray beam. What portion of the spectrum is most affected by the addition of aluminum filtration? I was thinking it was D because I thought that filtration affected more of the lower energy photons, and I thought that was what D was representing.
And
But
no, you're right. It's just that you read the graph wrong.
yeah, I
The
know.
lower that was A.
Yeah.
Sorry.
No, that is what happened, but yeah, anyone want to explain it?
Oh.
Yeah, I also like guess the same thing as you. I was just like, what? And I like totally read it wrong.
Wait, so is the one at A, is that like the 0.0, and then like as you go up in the graph, the number of photons increases, and as you go right, does the energy of the photon increase? So this is,
Yeah.
oh, I see. I definitely see then how you guys did that. Okay, yeah, that's confusing.
I did the same thing too.
Okay,
You guessed it
I don't know what C is really. Is that like the P?
I didn't get the spike. Is that just the peak? The peak of the
I think so. So that means that
photon?
very few of the energy photons are actually reaching the peak, and most of them are like either drastically below it or just
Yeah.
barely above it. So the peak is really very minimal.
Hmm.
So just to clarify, 0 would be over here, would be lower energy photons. That's why
Yeah.
it's definitely read that wrong. Okay. And then the last one is another relationship. How does decreasing filtration thickness affect the quantity of the X-ray beam?
So in this case, it would be the opposite, right? From what we were just saying.
Yeah.
A thinner photon will allow more of the photons to get through, like quantity of photons. But then this is going to result in both high energy and low energy. So we're going to get just a lot of everything.
Mm-hmm. A
Mhm.
lot more photons are gonna come through. Yeah.
Yeah.
Wouldn't that also give us like more scatter too, because we're getting a lot of energy, like low energy photons?
Yeah, I think so, because a lot more are going through to the patient.
Mhm.
A lot of direction changes, perhaps.
Yeah.
Is there anything else anyone wanted to add for this quiz or anything on filtration they thought was interesting?
No, I think this is nice because like Kimberly pointed out earlier, there was like, I thought about one explanation, but then like she reminded me that, it was like an inverse proportion. So it's kind of nice to just kind of talk it through because like that we're able to kind of see. So that was at least on my side, I think. I thought that was kind of cool.
Yeah. I think I said my two things, the atomic number. I thought that was good to see it on a quiz and then learning how to read a graph. But yeah, that's it.
All right, you guys.
Okay.
All right.
Okay.
Thank you.